Do you hear me? All right, thanks. Uh, Last time we finished with the YouTube video. I hope you were able at least to start to think about how to solve very simple examples. So this example was how fast Iron Man moves. Just a minute, I share it also. Here. What's your idea? How can we estimate the speed from this movie? I had several other questions like calculate the speed of Iron Man, altitude of the portal, what can be the weight of Leviathan. From my other students, I got some nice ideas how to start with. For example, if you try to see where Iron Man's uh, was flying, and you also measure the size of the blocks from these two information, plus checking how fast, oops, how long does it take to pass one block, you can estimate the speed of Iron Man. All right, the presentation one came back. Yes. All right. I also ask you to download the Firefox. Firefox is a simple tool for your mobile phone. I've saved the screenshot here. If you download it, you can, for example, use the sensors in your mobile phone. For example, if you click on the pressure, you will see how it collects the data, and on the lab, we can measure a few things based on this simple application. All right, so that was the story of the last lecture. Let's go further. What about units? Uh, you can imagine several hundred years ago there was lots of different units in, especially I know only the European story in Europe. For example, the length of the foot, the length of the arm, and so on. But that was different from country to country, and also inside one country, it it could be different. Um, John Wilkins was the first scientist. They tried to uh, unify the oops Wait a bit. Try to unify the systems. Uh, he said we can't do any science or not even we can't operate a country without having the same units. So at the end of the 19th century, uh, they've started to unify it, and the first unified unit was the meter. It was in Napoleon's time, so Napoleon said that in my country the meter is that one. So if you just walk in Paris in the riverside, you can find it somewhere. This is the meter. How can you, for example, share the meter? I mean, if we are here in Debrecen and this meter is in Paris, how can you bring the meter, the length of the meter here? Of course, at that time, you had to go there, bring your own rod, and do the scratches that represented the meter. That was not precise enough. Therefore, later, not that late, so therefore, they said the platinum iridium is a very stable metal. They put this metal rod in an air-conditioned room, and they said this is the meter. If you want to go there, you can copy it. Later in the 20th century, um, there was a technically a big conference where they fixed what are the basic units. The basic units are length, mass, time, current, the temperature, the light intensity, and the mole. You are pretty familiar. This is the 6 times 10 to 23, the pieces of atoms in a mole. Uh, every other quantities are so-called derived quantities. So having these basic quantities, if you are precise enough, this precision can go through to other derived quantities, like, for example, the density or something else. Let's go back. Yes. All right. Having a piece of metal represent the meter with that one is easy because you need only scratch that metal, but you can't really reproduce it. If you always have to go there to this standardized meter and copy the scratches from this piece of metal, it's not that precise. So uh, after this SI uh, conference, when they said the meter is the basic unit, we have to have it very precisely. And if anybody in the world want to know how long is 1 meter, it's not too convenient to go always to Paris and copy it. So therefore, they said the meter, if you can measure the orange-red light wavelengths from a krypton 86 lamp, and if you multiply it with this number, this is the meter. It seems to be complicated, but technically it's easier because anywhere in the world, in the lab, you can have this krypton lamp. With a filter, you can choose this orange LED light, and if you multiply it with number, anywhere in the world you can have the meter very precisely. Later, uh, they said it's also nice to having a lamp and filtering the light and so on, but what we know, the speed of light is a constant. It's not like something we can measure very precisely. It's technically a constant. So if you want to know the meter, and if you have a good number, how to divide the distance traveled by the light in 1 second, you can have the meter. Of course, that means you have to measure the second very, very precisely, because in this measurement, the precision of the meter depends on the precision of the time measurement. Uh, we use very different distances. Like if you go there, the diameter of the proton, which is the shortest distance we can measure. Perhaps you know the electrons are smaller than the proton, but technically right now, based on the all of your knowledge we have right now, the electron is a point-light object. Perhaps later we can measure it, perhaps this is 10 to minus 30 meter, but right now in all of the experiments it behaves like a point-like object, so therefore we can't talk about the diameter of the electron. So the shortest diameter we can measure is the diameter of the proton or neutron. This is 10 to minus 15. The distance from the Earth to the most remote known quasar, which is the most remote object we can see by our instruments, is 1.4 times 10 to 26. You can see we have to be very precise with the meter because we use the meter in a very wide range from 10 to minus 15 to 10 to plus 25, which is 40 order of magnitude. What about mass? They at that time also used this platinum iridium metal because that was stable enough. Perhaps you can imagine if you don't use a stable mm, material to representing the mass, this, for example, you can start with a piece of aluminum. If you put a piece of aluminum on your desk, the atoms of the aluminum on the surface can go into the air, so can be in uh, can uh, leave the the block, and therefore the weight can be changed. This platinum iridium is very stable, so technically till last year it was precise enough to represent the 1 kilogram. Of course, technically transforming this kilogram is very hard because you have to go there, you have to measure the weight, so you can bring your own platinum iridium block, and you can measure whether it's really the same mass like the standard. It was very hard. Later, the mass was represented by a very tricky measurement. You can click on this NIST, which is the office in the United States that work on the units, on the standards, and so on. If you click on it, you can check how the kilogram was introduced. So this is this shielded piece of platinum iridium alloy, and they handled it very careful. That was uh, the device. They standardized the weight, and later they said right now it's better to also fix it to the to a physical constant, which is the Planck constant. Also, in the case of mass, we can talk about very wide range of masses. So, for example, the mass of the electron is 9 times 10 to minus 31. You can be surprised. The electron has mass but has no diameter. It's still a mystery in the physics. How can have somebody's some mass without having any volume or diameter. That's something we can work on. And the mass of the universe, based on our best estimation, is 10 to 52. So in case of mass, we can talk about 80 orders of magnitude. That's huge amount of different masses in the world. Therefore, standardizing the mass, we have to be very, very precise. Otherwise, it's hard to do the physics in that wide range of masses. All right, time. Time, we live with time. Of course, we know what is one day from morning to morning, for example. But perhaps there are small differences among days and days. So even the length of the day can be slightly different. Also, the length of the year can be slightly different. And therefore, deriving the unit of the time from the solar day is pretty unprecise. They use the vibration of the cesium atom. This is the so-called atomic clock, and you can buy your own clock which is synchronized with some atomic clock, and therefore you can keep your time very precisely. Also, in the case of time, we use very different scales. So for example, we can measure how long does it take for the light to go through a proton, which is 10 to minus 24, and the age of the universe is 5 times 10 to 17. Here we also talk about more than 40 orders of magnitude. Since the time measured with it So the time measured with it, if you measure with that precision the length of the day, sometimes we can have plus minus a few seconds. Therefore, there are leap seconds in every, let's say, fourth of the year. Let's talk about prefixes. You've seen we use a huge order of magnitude differences, and therefore you should be familiar with the kilo, mega, giga, tera, peta, at least these 5 ones, and the milli, micro, nano, pico, and femto. In these prefixes, we always jump with 3. So kilo is 10 to 3, mega is 10 to 6, giga is 10 to 9. What are derived quantities? Of course, you know it, but let's define again. So if you have two quantities which are basic quantities like mass, and the volume is technically the cube of the length, you can say the rho, the density, by definition, this is this funny equation sign. By definition is the mass over volume. You can do simple calculation with this equation. Order of magnitude calculation. It's very important when you think about something you want to measure. You should know at the very beginning the, for example, the length you want to measure, not precisely, but only the order of magnitude. For example, if you want to measure the distance between your house and the school, you won't use ruler with a millimeter precision, but you can check it, for example, on the Google Maps. Or if you want to measure the size of your phone, you won't go to the Google Maps to check it. You will use a ruler. So knowing something before you measure by the order of magnitude can help you to find the best tool to do that measurement. In the order of magnitude calculation, I'm talking about, let's see, 0.00 86 is 10 to minus 2. 720 is 10 to 3. So we always, in most cases, we talk about the order of magnitude and not the precise number. For example, you can calculate the number of breaths taken during an average life. I solve it. So for example, by the order of magnitude calculation, the life is 100 years, 1 year is 400 days, 1 day is 25 hours. To have nice order of magnitude estimation for the hours in a year, 20 times 20 minutes, 6 breaths per minute, you can measure yourself how many breaths you do in a minute, and sooner or later you can have an order of magnitude calculation, let's say 4 times 10. You can think about simple things, for example, uh, how many steps you need to go from your home to school. What is the normal form? The normal form is a number in the range of 0 to 1. Oh, it's 1 to 10. Sorry, technically it's 1 to 10 minus something. This is the coefficient. Oh, I will check it. I will. And the rest is expressed by 10 to something. So perhaps you know this is uh, the formula for the gravitational force. This is a constant, this capital G. This is my mass. This is the mass of the Earth. And this is the distance between the surface where I am and the center of the Earth. If you can do this calculation, you can have I push the floor with 7.8 times 10 to 2 Newton. On the lab, we can use how to calculate with these normal forms. This is also exercise for the lab, and try to think about it before the Wednesday and Thursday group. How many carbon atoms are in a piece of chalk? And what is the weight of the CO2 emitted by a car? You can think about how can you estimate or how can you precisely calculate what is the um, weight of the CO2 emitted by a car by using the gas consumption of the car, how many kilometers you pass a year, and so on and so on. Try to collect good numbers and we'll do the calculation. Let's define two important things. In physics, when you want to say something, you have to say the number and the unit. For example, the length of the table is 1 meter. 1 is not enough, you have to add the number, the unit. Describing something else, for example, the position of your phone in the room, you need a coordinate system, origin, axis, and so on. It's represented by a vector. A vector has a number like 1 meter plus direction. We will see some example. The easiest example to understand what are the differences between displacement and distance, if you go from A to B on the path like this blue one, oops, your distance is the path you did, and the displacement is only the position B minus position A. So the vector from the A to B. How can we quantify it? We always need a coordinate system. Coordinate system means usually we use Descartes or Cartesian coordinate system. In some cases, it's easier to calculate with polar coordinate system or spherical coordinate system, or there are very different coordinate system. So always we need an origin and axis. And we will calculate with vectors. Let me show you what I mean. So vectors has always a starting point and an end point. The vector when you write a vector, you always have to put a small arrow on the top of the vector character. Here this is A, and by having a coordinate system like this one, here we have the origin, we have an axis x and the perpendicular axis y, and if you want to calculate the x component of the vector, means you project the vector to the x-axis, and this is the x component, and you project the vector to the y-axis, and this will be the y component. Adding two vector can be shown by, so this is A and this is B vector, and if you want to calculate the A plus B, means you have to push the starting point of the B vector to the end point of the A vector, and then connect the starting point of the A and the end point of the new B vector. Here I showed you a spherical coordinate system. In this case, just a minute, I have to plug in my laptop. It's done. So in the case of spherical coordinate system, we are talking about distance from the origin, this is r, and the angle between the line connect the origin with this point, and this is the angle between the z-axis and this line, and if you project this line to the xy axis, you will have another projected line, and the angle between this projected line plus the x is the phi. So r, theta, phi can be also represent a point like x, y, and z. Please look at this calculation, how we add two vector. Adding two vector means adding the component, multiplying with a constant means multiplying with its component. The length of the vector is the square sum of the components and square root it. We can talk about unit vectors. Along the x and the y, you also can put an I and j, and along the vector z, a key vector. These are the unit vector. They are perpendicular to each other and their length is 1. So these are the basic vector, unit vectors. In some cases, these are very important, especially describing the position or doing calculation with the positions. This is the right hand rule. There is a so-called, let's go back. Multiplication of the vector. There are two kinds of multiplication. What is the dot product or scalar product, and the other is the vector or cross product. The cross product is pretty important at some forces. We will practice it in the lab. There is a so-called right-hand rule. So if you have an A vector this direction, B vector this direction, the A cross B is always perpendicular to the plane describing by two vectors. Alright, so if we can create a coordinate system starting with the origin and then x, y, z axis, these are all perpendicular and follow the right hand rule, then in this coordinate system we can describe the position of every point, technically in every body. Just a minute, I double check, yes, the streaming is still okay. So the position is the location of the particle in the coordinate system. So for example, if this is my coordinate system, the origin is at 0, and this is one dimension, we have only x-axis. If we have a point here at 5, we can say my position is 5 meters. How can I define the displacement? You remember, displacement is a vector. If we have a vector describing my initial position and the vector describing my final position. The vector of the final position minus the vector of the initial position is my displacement. The displacement, for the displacement we use this capital Greek letter delta. This is the changes of the position in a macroscopic, in a measurable time. If you are familiar with the derivation, we can talk about changes in a infinitesimal short time, which is not measurable. Alright, so once again, let's imagine you are at 5 and go to 15. Your displacement is plus 10 meter. If you go back from 15 to 5, your displacement is minus 10 meter. But if you move from 5 to 15 and go back, your distance you did is 20 meter, but the displacement is 0 because moving from 5 and going back to 5 mean the initial vector is 5, the final position is 5, 5 minus 5 is 0. What is average velocity? If you observe a particle which changes its position by delta x in a time interval delta t, and if you derive this delta x with this delta t, you can have the average velocity. Technically, in y-dimensional, this is a number. In 3-dimensional, this is also a vector. What are the differences between velocity and speed? By velocity, you divide the displacement by the time, and by the speed, you divide the distance by the time. Graph of the motion. Sometimes it's very useful to create a graph about the motion. So in this case, let's try to understand how the particle moved. At t equals 0, I'm at 1. So here on this axis, I'm here. And in 3 minutes, I move from 1 to 7. What is delta x over delta t? Delta x over delta t, delta x is from moving from 1 to 7. The delta x, the displacement is 7 minus 1, which is 6. And the velocity is delta x over delta t. We needed 3 minutes. Oh, sorry, second. Moving from here to here, moving from 1 to 7. The delta x is 6. The delta t is 3. In this case, my speed is 2 meters per second. On this red zone, my position is always 7. At 3, 4, and 5, my position is 7. What can be the velocity? Since the x is 7 at the initial and 7 at the final position, delta x equals 0. 0 divided by 2 is still 0. So here my velocity is 0. And in this case, I went back from 7 to minus 5. The delta x, my displacement was 9. Wait a bit. Now it's 12 divided by the time interval for this motion is 5 to 6 is 1, 2, 3, 4. So in this case, my velocity was minus 3 meters per second. What is the average velocity? If this is the start point and this is the end point, the total displacement is, so final point is minus 4, minus 4 minus 1 is minus 5 meter. The time I used is 10 seconds, so the average velocity for all this motion is minus 0.5. What is the speed? Speed is the distance, so if I go from 1 to 7, my distance is 6, then I stayed at 7 distance till 6 meter, then I went back from 7 to minus 5, the distance was 12, so the total distance here we have a plus 6, so this is Here we had a 6, and here we have a 12, that 18. So this particle, the distance of the motion of the particle was 6 plus 12 equal 18, divided by 10, this is 1.8. So the average velocity was minus 0.5, and the average speed was 1.8. There are differences in speed and velocity. Also, if we can draw the motion, we can do it upside down. We will do it on the lab. I will give you a formula, a function, how x changes via t in different time slices, and you should draw it and say what is the speed here and what is the speed there, what is the speed, what is the velocity, and so on. This is only for the lab. Here we talked about average velocity and average speed. We can, if we change this delta t, or I don't know whether you're familiar, this is limes, means I start to use smaller and smaller delta t. Why is it important? Because from this average velocity, by changing the delta t to an infinitesimal small number, it never reaches the zero because you can't divide it with zero, but you can go to very, very close to zero, and this is the so-called derivation. You can derive the x with t. In graph, this derivation means the slope of the line. In the case of line, the derivation and the slope is the same thing. In case of, let's say, 2 times 10 to square, it's different. But in the case of lines, when the speed was a constant, if you derive the xt function, you will get technically the speed. What is the instantaneous velocity at the given time? So for example, at 1, if you derive this function, the speed will be 2. What does it mean, 2? For example, if you take a closer look at, I will share this presentation after this streaming. If we see, if the velocity is 2, means in 1 second, in any 1 second of this motion, you change the position with 2 meters. And you can see here, going from 0 to 1, you will go to 1 to 3. The displacement is 2. From 1 to 2, you go from 3 to 5, the displacement is 2. From 2 to 3, you will go to 5 to 7, the displacement is 2. This is what 2 meters per second means. Also, in some cases, not only the position of the particle changed by the velocity, but also the velocity of the particle changes. We can also talk about average acceleration by measuring the changes of the velocity divided by the time interval. And if we also take this lim as delta t goes to 0, we can derive the v function, and you can have the acceleration. We can talk about acceleration, deceleration. If the acceleration is positive, means the velocity of the particle will be bigger and bigger. If the acceleration is negative, the velocity of the particle will be smaller and smaller. For example, this is a constant acceleration. So, let's start. Constant position. Constant position means you can imagine the horizontal is the time and the vertical is the position. If at every time you are in the same position, means you stay somewhere, let's say at 7 meters. In this case, the velocity is 0 and acceleration is also 0. Constant velocity means the graph of your motion is a straight line. If you calculate the slope by deriving, for example, the function of the xt, you can have the velocity, but since the velocity does not change, the acceleration will be zero. The constant acceleration means not only the position changes by time, but if you look at this plot, the slope of this curvature, this is a t-square function, is different. Means at different time, the velocity is different, the velocity increases. So you will have a velocity graph like a straight line, and if you calculate the slope of the velocity, you will get the acceleration. You should be very familiar from your high school uh, with these formulas. There are equations, so if we know what is the acceleration and the acceleration is a constant, based on the final position, initial position and acceleration, you can calculate the final speed, the final position. These are the formulas you are familiar with. Right now at the university, we will use integration and derivation. So I'm very happy that you can calculate the position of a particle at constant acceleration, but right now we will do derivation integration to have this value. Free fall. The most typical one-dimensional motion is the free fall. In this case, we don't have to think a lot about coordinate system and so on, where we start the body. This is the origin, and the path falling down, that can be the x-axis, or up to you, that can be the y-axis or z. Here we have also a nice video, so you can check. This is Brian Cox, and just check it at home. Why was it so hard to believe that independent of the mass of the bodies fall down with the same acceleration? You will see it in this video. Galilei. Galilei was a great guy, so we can talk about modern physics starting from Newton, but Galilei was the first guy used the same method to measure something what we use right now. So without any preconception, they just want to measure something, and by measuring something, they wanted to understand the physics. So the way how we do the measurement is the same, but right now we use lots of electrical device to do the measurement. Alright, so we will solve example with free falling object. We know the G is the symbol of the gravitational acceleration. It's 9.8, 9.81. For the faster calculation, we can use 10 meter per second. If you want to speed up something, of course, you need a large acceleration. In some cases, you can have a trick. So if you have a body going with, in this example, with the speed of 50, and you throw a ball with the speed of 30, you can speed up your ball with 2 times the speed of the heavy body is 50, which is 100, plus your original 30 up to 130. Why is it important? Because in some cases, if you want to go far with a satellite or something, you can use it. This is the so-called gravity assist. Means there are lots of speedy, heavy body in the solar system, planets, moons, and by use this gravity assist, you do not have to accelerate your rocket by fuel. You also can use the motion of the heavy bodies to speed up. Especially important when you want to go very far, yeah, like to the gas planets, so Jupiter, Saturnus, Neptunus, or if you want to leave the solar system. For that case, if you want to wait hundreds of years, what you can, so with your normal fuels we use for satellites, to speed up satellites, or accelerate satellites, you can't reach that high velocity, but with the gravity assist, you can be faster and faster, and the travel from Earth to the edge of the solar system won't take that long. One nice example, scenario, the comets came very, very fast, so 40 kilometers per second. It's very hard to reach even in the even outside the Earth, so where there is no air resistance and so on. It's very hard to reach that limit. So therefore, at the NASA or European Space Agency, they use this gravity assist, let's say 10 or 20 times to speed up the satellite to have the same speed as the comet to fly parallel. This can be long, so sometimes one travel of the satellite, one to fly parallel with the comet can be 10 years old, 10 years long. All right, so what is important? Important to me is understanding the coordinate system and playing with vectors, adding, subtracting, multiplying, lengths, and so on. This is very important in the physics. Then we use the vector to describe the position. And by the position, we can talk about displacement and distance. Try to separate these two things. And from that, we can um, define what is velocity and speed. If you are not familiar with this limes, we will talk about at the lab. This is very important because if you have the function of your x, you can have the function of the v, and also if you have the function of the v, you can have the function of the a. This is very important in the kinematics we are learning right now. So, if you are familiar to draw a plot describing the motion, so you can move something on your table, and by drawing this graph or by formalizing the motion by equations can help a lot to understand the physics. And we will solve an example by filling Foley object at the lab. So I think that's all. Now I switch off the streaming and you can ask via Discord.